is the shell. The machine learning is the albumin, and deep learning is the yolk. So when you look at AI, talking about artificial intelligence, which is the ultimate goal, you are mimicking human behavior and cognitive learning. So what are you doing? We are trying to look at how the human brain works and try to replicate that in machines. So look at the analogy I gave here, the concept of what a self-driving car. And we're beginning to see things like that, like the Tesla car, you can put your instructions, create your navigation links, and you find out that the car takes you to your destination. Then you have the machine learning, which is the albumin. I call it the albumin. It's the statistical method. So this is the tool or the methodology involved. So you are trying to improve your predictive accuracy through what? Experience and data. When it comes to the concept of machine learning, it would not work if there's no data. So data is like the fuel. So I'd say an algorithm calculating optimal traffic routes. Yes, look at your Google map. You put in your destination, it tells you in 5 minutes or in 5 kilometers, turn left, in 2.3 kilometers, turn right, and things like that. So it calculates your route, your traffic route. And you can also check where are the traffic grids, where I need to avoid traffic and things like that. So it's like a predictive accuracy that learns from data and notes those experiences it has learned from the data that you have given it so that you don't repeat the same mistake. Then we go to where we really want to talk about today is deep learning. This is like a computational engine. I talk about multi-layer neural networks, mimicking the human neurons. So, and why are we doing this? We want to execute complex pattern. I talk about complex pattern recognition. I said the sensory system instantly identifying a pedestrian in the dark. You begin to say things like that. So we talk about deep. So when you have artificial intelligence is the body that covers machine learning and deep learning. But deep learning goes now beyond just a predictive model, but now a model that begins to move or behave, because our goal is to mimic the human behavior and carry out cognitive logic. And you can't do that just with your statistical model. You need a computational engine that can do that, and that's where deep learning comes in. Okay. So introduction to deep learning. I said deep learning is a subset of machine learning that uses mathematical functions to map the input to the output. Yes. Unlike your machine learning, you already know the output before the input, but this is the other way around. It maps it. So these functions can extract a non-redundant information or pattern from the data, which enables them to form a relationship within the input and the output. All what I've been saying is this is known as learning. And the process of learning is called training. You pick up a particular data set. Okay, we have a data set that contains the picture of a dog, a cat, and a cow or horse. So you train the data to begin to recognize patterns, to begin to recognize complex relationship between those data that you have given. How does the ear of a dog, how does it look like? How does the ear of a cat looks like? How does the foot or the paws or looks like? So he begins to look at those kind of patterns, those relationships. Oh, for a cat, it looks puffy, the head looks a bit roundish. For a dog, it looks it looks protruding and things like that. Oh, what differentiates a dog from an horse? Okay, dog has 5 paws. An horse has hoofs. Those are things it looks like. So it learns patterns. And through that process, when we say learning, the human brain is learning. Our deep learning model is doing what? It's training. So it's an act of learning. So let's look at this. Feature extraction bottleneck for a classic machine learning model. When you look at your machine learning model, this is what you have given it. This is a car. You can see all you need to do is, okay, look at it. What shape? What does the shape of the car looks like? It does its feature extraction. Okay, it has wheels, 4 wheels. It has 2 side mirrors. It has 2 wipers or shield blades for wiping. It looks at a tail light. It has an headlamp and things like that. So I say classical machine learning requires human engineers to manually, yes, in fact, that's different. Now, you manually put in, okay, and say, okay, decoding the rules for red or octagon to identify a stop sign or things like that. So you tell it, oh, see, it's something that has what, 4 kind of tires, has a tail light and an headlamp, it has 2 side mirrors. That is a car. Then when it is a bit bigger in size or shape, that is what? That is an SUV or things like that. But you need to put that before sending into your classification model, before putting that into your classification model. But when it comes to deep learning now, you allow the machine itself now, the machine itself to do the work. You don't need a feature extraction person now. You don't need yourself to give it or to help it to extract features. Both the feature extraction and the classification is done by the model itself. So you begin to hear things like supervised learning and unsupervised learning. So when it comes to machine learning, you talk about supervised, but most when it comes to deep learning, it becomes unsupervised. So I said deep learning bypasses the human bottle length. It learns to extract what? Non-redundant patterns and classify the data simultaneously through training. So when you put the data, you put a lot of car images and things. Okay, you put a car, you put a motorbike, you put a truck. So it begins to look at, you can see, what we need to do is, or we need to get which is a car, not a car. So it develops its own pattern itself, extract features itself, node by node, patches by patches. It picks areas itself. So it looks at the wheel. It counts, okay, the wheel of this looks this way. It looks like the height from the floor to the body of the vehicle. It looks like the tail light. It looks for a lot of features run. It takes it. You begin to hear. So when you hear things like convolutional network, so it begins to run patches using a kernel, which is called a filter. It begins to look like this. So the way I'm moving, you can see the way I'm rotating my, what's it called? My mouse. So you begin to see, giving you this extraction like this. Unlike the machine learning, it just picks this hole. And oh, it has tires here, tires there, has tail light. Each one comes to the tire when it comes to deep learning, even from the tires, it picks patterns to see. Oh, for a truck, it might be the ridge or the space on it is different for a car and things like that. So you see that the machine does both the feature extraction or the model does both the feature extraction, but for machine learning, you have to help with them before putting it into the algorithm. All right. So why deep learning? Because those are some questions that we should ask ourselves. Why are we talking deep learning? Why are we going beyond machine learning now and talking deep learning? Okay, I said here, so when the amount of data is increased, machine learning techniques are insufficient in terms of performance, and deep learning gives what? A better performance like accuracy. Yes, it's the truth. There's an amount of data that your machine learning algorithms or models can handle. So I've just done like a matrix here. There's a matrix here saying performance and amount of data. So when you look at this, you can see when it has this, your traditional what, machine learning can handle it. When it goes to the next one, which is the blue, you have your shadow neural networks. When it comes to your green, you see, but when it comes to optimal, large size and amount of data set, your deep learning model can handle that. So why? Your algorithm advancement, GPU computing, and availability of large training data. That's why we need deep learning. There are some models that for you to train them, they are computationally high. You will need an high performance computer. I don't know how many of us have heard of HPC. I'm sure we are all used to HPC. So high performance computing, where you use your SSH and to call, you schedule your jobs and things. We have a kind of machine that can process close to 18 terabytes, 80 terabytes of data set at once, put them on queue, and processes are going on. So you need what? A deep neural network. All right. So what is driving the deep neural network era? Those are the things I've spoken about anyway. I've spoken about algorithm advancement, breakthroughs in mathematical modeling and propagation. Yes, a lot of advancements are coming in, especially in the health sector. Just like Div told you guys, I work on sickle cell anemia and pneumonia. A lot of diagnostics are coming up, and the medics, they want to carry out diagnostics in very, very superb time. Then the hardware shifts. Yes, you see that there's parallel processing now, massive parallel processing. We've gone from the days of Pentium. Now we are even not talking about I-core anymore. You find that in the next few years, I-core or i7 core, i7 or whatever they are called, they go out of phase. Then there's big data. Data is everywhere. Somebody once said data is the new oil. Data is everywhere. Explosion of the internet. A lot of data being dumped around. Even people don't even know what to do about them. So labeled, and you are finding out that they are massive. Some are labeled, some are not labeled. So people are just, so data is scattered around. So we need deep learning to be able to analyze what large amount of data sets. So how does this deep learning work? That's something that we should look at. How does this work? I said deep neural networks have what? Multiple layers of interconnected artificial neurons or nodes that are stacked together. Exactly. When you see the human neuron, so now instead of we are mimicking the human neuron to do what we want to do, but now we are not multiplying that. So that's why you get the word. When you hear deep neural network, it's just layers, multiple layers. So not just one node now, carrying out feature extraction and what do you call it? And classification or your regression analysis or whatever you are doing. So each of these nodes action that performs extraction and mapping of information. So you see that, and there are always three layers. There are 3 layers to your deep. You have your hidden layer. Okay, so I was talking about big data, and I think I was talking of the big data, and I said there's data everywhere. And someone says, and a lot of people say it now, that data is the new oil. So we need deep neural networks or the deep learning models to carry out what? To help us to what? Analyze this data, give us meaningful insights that will be able to solve what? Real world problems. I tell people you don't analyze data just because you want to, out of you just trying to be, to have fun. We have to use this data to solve problems, and they should be real world problems because there are loads of data out there. All right, so I now spoke about how deep learning works. I said it works with multiple layers of what? Interconnected artificial neurons, which are also called nodes. So they are layers. So when you talk of models like ResNet 50, when you see the word 50, it's telling you it has what? 50 nodes. You talk of DenseNet 121, 121, things like that. So the layers, the convolutional layers are multiplied, are in multiples. And I said each of these nodes has simple mathematical function. They are usually a linear function that performs extraction and mapping of information. Yes, it extracts basic features that you need and map them together. And that's why you understand why it understands that, okay, this is a picture of a dog. This is a picture of a cow. This is a picture of a horse. And I said your deep neural network has 3 layers. You have your input layer, your hidden layer, and your output layer. All right, so this is it behind your deep learning. You can see. Can you see this now? So this is your input layer. You have your data set, might be more than 1. So it's x of 1 to what? To x of n. You have your weights. You score them, so it brings them and analyze. When you talk about you analyzing or talking of scores or your activation or your activation function, you're talking of things like your ReLU, which is your rectified linear unit, which is one of the most common used activation function in deep learning and machine learning, especially in your what? Artificial intelligence. So what does it do? When you talk about your activation function, they transform your input values. You transform. So when what you are put in, you put in your image or your numeric data. So what it does is that what it keeps them into what? Positive. It brings them and says it keeps positive values and turns negative values into 0. So it works with positives. It comes in, if x is greater than 0, your output is x. But if x is less than equal to 0, your output is what? Is 0. So that's where you find car or no car. So when it breaks down, it breaks all the images. Even when you put an image, it breaks them into a mathematical function. And the function is f of x is equal to what? Max open bracket 0 minus x. I believe in our last version, we'll be able to do some practical, so you see what I'm talking about. All right. So imagine your input for your numerical input of your image after it has done the processing, carry out the score of the patterns and features, and you have -5. When you have -5, your output will be 0. When you have 3, your output will be what? 3. When you have 7, but what it's saying is that, okay, there's a positive match. When there's a negative match, then it is not. It is either it is a car or it is not a car. It is either there's pneumonia in the chest X-ray or no pneumonia. It's either the patient is he has sickle cell, or the patient has no sickle cell. All right. So you can see your second layer also, which further does. So when you look at your first layer is the input layer. The second layer is what? Is the hidden layer. Then you have your third layer, which is called the output layer. So you can see that complex, and you see multiple units. Can you see hidden units? Can you see that this unit working on this core, working on all cores, all units keep on multiple layers trying to check, oh, did this layer make a mistake, or this layer could not undo this particular feature? Let me help out. They keep on mapping one another. So that's why you say complex mappings. Complex mapping, looking around, no faults. We must to the barest minimum to be sure that what has been classified correctly. Then, when everything has been done, you have your output. This is a car, not a car, likely a car. You will also find that when you are doing multi classification, you have binary and multi classification. When it's binary, you have yes or no. But when you have multiple, it's either there's a yes, like especially when you're looking at things like severity. You're trying to look at severity of a pneumonia in sickle cell anemia patient. So you might have mild, you might have a moderate, and you might have severe. So this is just what your deep learning structure looks like. All right. So you see, mapping biological inspiration to mathematical reality. So we'll be talking about neural networks. So somebody will have been wondering, what is Oluwole talking about? So you could see what we did actually, or what scientists did, was just to mimic the human neuron. I'm sure they will have some biological students, and so you can see the human neuron. You have your dendrites, you have your axion, and your cell body. So you can see our dendrites are what? Our input and weights. So you can see our nucleus here, which is what? This is where our bias, we try to avoid bias in the image. Then your activation function, which is what? Which is your axion. Then the cell body, you can see this is the cell body. Then you have your output. Can you see? So that's what was done. So I said the biological perspective assumes that we can reverse engineer the human brain to build intelligent system. So the engineering reality is that modern deep learning is fundamentally a mathematical model. It uses a linear function to map inputs to output, extracting what? Information step by step. So you can see it picks information X1, weighs it, puts it into the bias. One of the things you try to avoid when you are trying to train your models, avoid bias. Because when there's bias, there's always problem of what? Maybe your model is overfitting, or what is underfitting. So there's no magic here. All that's been done is to mimic what the human brain looks like, tissue. Now let's replicate that in machine. And how do we do that? We will always need a mathematical model. All right. So let's go through introduction to neural networks. Introduction to neural networks. What are neural networks? I said they are modern deep learning models. That use artificial neural networks, or simply neural networks to extract information. Everything I've been saying all true. So these neural networks are made up of this simple mathematical function that I showed you, which are stacked on top of each other and arranged in form of layers. So that's where we have our layers. So on top of each other, you have your input layer. You can see just your input layer. You have input, which is 1, 2, 3, 4, 5. You can see the way it has mapped. This image has been mapped with this hidden layer, your convolution layer. Everything is mapped. So you find a complex mapping till you get to your final destination. So you keep on finding your input layer. Your hidden layer now can be 150, just like your ResNet 50. It has one input layer. So when you have your hidden layer, it will be almost 50. Then you have your output layer. So complex mapping has been done. So it gives them a sense of depth. So that's why when you hear the word deep learning, unlike just extracting, I myself or you as a scientist extracting features for your machine learning models, it keeps on extracting even plausible features, just to be sure that every area has been touched. No stone is left untouched till you get to your final destination. Because at the end of the day, we are trying to say, is this a car or is this not a car? Is this a horse? And we won't want our model to see a zebra and classify a zebra as an horse. You know, that model has missed it completely. All right, so let's look at this. So decoding the hidden layers of a neural network. Like I said, you have stack of multiple layers interconnected together. Each layer applies a simple mathematical function to to start looking for how to extract complex and non-redundant. When you talk about non-redundant, we don't want something that will not add value to our mode, to what we are trying to do from layer before it. Then it begins to transform the raw data into high level conceptual understanding. So you see now, so when you feed it, you feed a raw image. This is what I take a picture of div and I say, okay, I want to know who looks like div. So I mix a lot of pictures together and I train my model on that. So what it does, what it sees is this. It sees this like this. That's what, because our models always they understand, what's it called? Understands in numbers. So these pixels are broken down into numbers. Into numbers. So that's what is going on here. So you now see now there's a break now. You see that this looks blurry. What has it done? These are pixels. So your model applies what? A filtration on each of these model, node by node, these boxes one after the other, goes through this dark box, analyze what is this area. What are all the structures on this area? So you can see it looks blurry like that. So from there, it begins to understand the eyes. Okay, underneath, can you see this is underneath of the eyes? The base where you have your eye bag. Maybe your eyes are swollen, you have your eye bag. It begins to look at it one after the other till it gives you a picture of the complete eyes. It starts from one of the nostrils. These are, when you break this, I draw lines on this. When I draw grids on this, you see. So it picks them pattern by pattern and start merging them together. So before you know, you get your real image. So if I said differentiate now and I train my model on images between a male and female, so it knows how to do that. So it's going to classify male. So it tells you any image that has these features is a male, and it gives you the second word is what? It's a female. So you can see raw pixel data to combine those edges and lines. You combine them together to give you distinct facial features. Then at the end of the day, you synthesize the features to identify a specific face. So I can give my model, train my model and say, differentiate between a black man and a white man. Differentiate between somebody who is of color, things like that. So you begin to differentiate between a dog and a cat. Differentiate between a zebra and a horse. So these are the complex things that go. Each edges are picked one after the other. Unlike machine learning that just looks for okay, the ears are long, the eyes are oval, the light pink or things like. No, deep learning goes deeper than that. It picks in grids. Look at edges, look at shadows, look at lines, look at patterns, even to you to know somebody whose ear or a ear is longer than one. Things like that. It matches complex patterns together. All right. So what are the types of neural networks that we have? You have what you call your convolutional neural network, which I call works on spatial data. When I talk of spatial data, works on images. Then what is the real world tech example? You have your Tesla autopilot vision. Yes, a self-driving car. Look at the structural pattern. You can see that it acts like a grid, just what I just explained to you now. So it picks grid by grid. Then you have what you call your recurrent neural network, which is the RNN, which works with time and text, your sequential data, just like your Siri or your predictive text. Have you ever imagined you are trying to type now, you've been typing on your keyboard, and all of a sudden you are typing to maybe your friend and you want to say, I am going to. It predicts the next thing, I am going. It tells you to. Then it gives you options like market, to the shop, or to school. So those are recurrent neural network does that. Then you have your transformer models. These are for your large language models. Your large language models like your ChatGPT, things like that. So we call them parallel sequential data type, which is the context. Then you now have what we call the generative adversary network, which is your GAN. Generative creation, like your deep fakes. So you have what you call your generator and discriminator. So the generator picks in the image, then discriminator begins to now identify which has been taken by an original camera, or which has been deep faked. So as we go on as I go on, I'll begin to explain them after the other. All right, so let's look at the convolutional neural network. I have a basket full of apples, fruits. So I said there are two apples in the picture, or there are different types of fruits. Now, train to begin to understand which is an orange, which are oranges, which are fruits. So you can see by the time you are training, you train your model, and your model gives you your output. So begin to differentiate. Oh, they are red apples. So if they are also green apples, it classifies them into that. So that's what your CNN does. So this is just a simple illustration as we go on. So what are convolutional neural network, which we call the CNN? I said they are primarily used for tasks related to computer vision or what? Image processing. They are extremely good in modeling spatial data such as your 2D or 3D images and videos. They can extract features and patterns within an image, enabling tasks such as image classification or object detection. Look at this. You serve your model pictures of cats and dogs. It sends it into your input layer, sends them into your hidden layers where all, pattern recognition, spatial, non-redundant spatial processing and things like that. So it now tells you when you have your output, you are telling it, is either you're asking object detection with these two different data sets I've sent to you, or we have trained you on, which one is that of a cat? Then you can also have a binary classification, image classification, differentiate between a cat and a dog. So you can see as simple as that. So just to explain what your convolutional network preserves, that it preserves a spatial relationship in visual data. Unlike I was explaining to someone before the class, and I was telling her, I said, this is just the difference between machine learning and your deep learning. Your machine learning picks this whole picture and looks for patterns and just picks it at once. Oh, long tail, long ears, stripes. No. Your convolutional network does not do that. It applies what you call kernel. Kernel are what? Like filters. So it's just like you having a filter or let me give a magnifying lens. Thank you. That's the word. I have what's written on a paper and I have a magnifying lens to pick the alphabets one after the other. That's what your kernel does. So your kernel does just not go through this at once. It starts from pattern. It starts from the OOF and divides these OOFs into grids. So you can see picking these stripes now. So it looks at and begins to count for a zebra, even with the stripes. How many stripes are on the leg? What is the distance between a stripe and the other stripe? Then what are the shapes? Is there a place where it curves in, it caves in, or it curves outward and things like that? It does that starting with just the hoof up to the leg, to the knee, like that. It does this. So that's why you see that I say it's computationally intensive. So you might be training a model, and if you don't have a high performance computer, you might be trying to train a model and you're training. There's a model I trained, I had to go pay for high performance. I've been training 7 days and I wasn't done. I was training, trying to do severity of pneumonia in under fives. It took me 7 days and I was still training because it was picking patterns and patterns, feed into your what you can see, we call them feature mapping. It begins to pick that till it puts it into your what your hidden layer, try to check and see. So you see at the end of the day, when you have your output, which I call output probability vector, this picture looks like what? 0.7% of zebra, 0.2 of us, 0.1 like a dog. So we look at the higher probability and say, yes, indeed, this is what? A zebra. A zebra. So I said the scanning kernel, it analyzes the virtual data in a localized overlapping patches. That's what I meant, patches. Like you're putting your magnifying lens over an image you want to see. So rather than processing the entire image at once, which I explained, the mechanism strictly preserves the 2D geometry and relative position of the pixels. So he just draws a grid around here. Draws a grid here. Pick them box by box until it has gone through all boxes. It will not stop. Then he moves it again. So that's what your kernel does, like a filter. He moves it to the tail area, draws a grid over it. It could be a 2x3 matrix, 3x3 matrix, 4x4, whichever you have specified. Then I talk about the spatial feature extraction. I said, this localized processing makes your CNN highly effective at modeling structural data for object detection, autonomous driving, and identifying anomalies in radiological X-rays. Yes, I work on X-ray images, so I don't joke with my CNN models. All right, let's talk about the recurrent neural network. So you have your input, you have your model, which keeps walking around. It keeps going recurrent. It comes back even after it has done what it needs to do to be verified, like revalidation, before you get what? You get an output. So I say your recurrent neural networks is a type of artificial neural network designed to process sequential data or time series data by using hidden states as memory. Yes, it memorizes. What did I get from here? So I said, unlike the feed-forward network, your RNN passes your previous output back into the network again, allowing them to utilize concepts from your earlier inputs to inform current predictions, making them ideal for language translation, speech recognition, and stock forecasting. If you notice now, for those of you that use Siri, when I first got I used my Siri, it took time before it could take my voice now. Now I realize that even with my mother tongue, my Siri understands that it's me. And better now, my Siri pronounces my name better now. When it started with Oluwole. But now it calls me and you think my Siri is from my hometown. It says Oluwole, and I'm like, wow. So it learns, because I've been speaking, it's been trying to understand my intonation, it's been trying to understand my mother tongue, been trying to understand where I came from, things like that. Oh, this is what it speaks. These are the mannerisms or gestures or pauses I have when I talk. So this is one of the major, and see, they work on what? Language translation. And that's why you have language translation models now. I speak French and you have your translator. It tells you in your language and it's perfect without even missing the tenses and mixing them up. Then you have stock forecasting or weather forecasting, things like that. Your recurrent neural network does that fine. So look at it now. Processing your synchronization data with what? Recurrent neural network. Talking about predictive text, which I was just talking about, or I explained earlier. How does this work? I said they are excellent for sequential data like text. As you type, the network processes each word in sequence. Yes, it looks at it. So it remembers the context of your previous word. You might have done some typing before and you have told somebody about 2 weeks ago, or you told your friend Andy or Kate 2 weeks ago, oh, I'm going to the market. So immediately you type again and it recognizes the pattern of, like, you have said this before and it says I, he waits. You type am, it waits. Going, then you want to put, it gives you to, then you put to, it says, oh, the next that follows is D. Then before that, you just see it gives you your option, asking you, am I going to the store? Maybe you went to the store about 2 weeks ago. Oh, so if not the store, let's suggest maybe to the park, or what? To the beach. So I said it learns the flow of language from massive data sets. Yes, it keeps on gathering data. How do you talk? How do people talk? What are common words that we all say? But it has a bottleneck. It can struggle with when the sentence becomes very long, context begin to get lost. So I say forgetting context from what? The earlier. So this is a problem we call the vanishing gradient problem. So this can lead to nonsensical predictions in the long form. So you find out that sometimes we call that hallucination. So it just gives you some funny things like you just delete and type what you want to type. But believe me, you type the right thing, it has learned again. So next time when you are typing a very long word, it begins to learn from everybody again to see. And with time now, you find out that this bottleneck with time will begin to give way, because your recurrent neural network keeps learning, going back. Oh, this was the way we did it the last time. Something changed, add it again up. Something changed, add it again. Something changed, add it. So you begin to learn like a learning curve is being achieved for every time you get an output. It goes back to train the model to say, oh, the output of yesterday is different from today. And things just keep going that way till you get your perfect. So I put examples here. You have your Apple keyboard, your Gboard, then you have your messaging apps like your WhatsApp, your Facebook, and things like that. All right, then we look at our generative adversary neural networks, your GAN. Your GAN, which I say works with what you call your generator and the discriminator. So I said there are frameworks that are used for the tasks related to unsupervised learning. Exactly. You use your gun. You don't want to give it any features or anything. You want the model itself to learn itself. I said this type of network it essentially learns the structure of the data and patterns in a way it can be used to generate new examples similar to what? To that of the original. So you bring in your training set, your reward image, sense it into the discriminator. You add noise also. Noise are unwanted elements, things you don't need. So they're like things that are not common. So you add noise image. You pass them into what you call a generator. The generator also puts it into the discriminator. So it begins to analyze, okay, this is the real image. This image that has been created also, it wants to look like, you can see it's blood. It looks as if it's the what? It's it, but it is not, because it goes deeper into it to check. Was this coined from this? Or this trying to mimic this? So your model what begins to do that. Then your discriminator now tells, no, this is an original image. This is a fake. Then it gives you, for this is a real image, and this is a fake image. And that's why you see now in the era of AI, if you are not very careful what you view online or what you are trying to do, you can get distracted and think what you are watching is real. I've had somebody come to me to say, oh, come and see. Oh my God, a train just ran over people and I just saw like a skip. Sometimes you see like some glitches. And I said, no, this is fake. No, he said, no, it's real. This, that, this. And I told you, look at it now. This guy had 2 legs and all of a sudden it looks as if he has 3 legs. So when you look closely, but there are some perfect deep fakes that if you are not careful, you are not an expert, you might not be able to detect that. Then we look at our transformer models, which I told you we use them in our large language models. So they are used for natural language processing, which power models like your BAT, your GPT, and your T5. You have your machine translations used on your Google Gboard to translate. Then you have your text summarization apps. I have what's it called? Your Grammarly and things like that. You have your speech recognition, which is your Alexa and Siri. You also have computer vision, which is applied in your vision transformer for image processing. So transformers are the key, are the in things now. You see a lot of things, transformer models coming up. So what are they? They are a new class of deep learning. Yes, they're just like what I've said. Excuse me. That is used mostly for tasks related to modeling sequential data, like your natural language processing. I said it is much more powerful than your RNN, yes. And they are replacing them in every task now. Your RNN, it was from your RNN that we brought about your transformer models, the limitations, the bottlenecks. So recently, transformers are also being applied in computer vision. Yes, I noticed that now. And they are proving to be quite effective than your traditional. So before you know it now, like my model now for my PhD thesis that I'll be doing my result very soon. So I'm not going to be doing a comparison of the new transformer models with what traditional CNN, the ResNet 50, the efficient net B naught, and the DenseNet 121 against Vision Transformer. So talk about their limitations, talk about why this surpasses that, then do an ensemble of the traditional CNN versus also your VIT. Okay, if they are standalone, what do they gain against the transformer? Can they beat them? If you combine them together, can they also beat your transformer model? So you can see it's a very, very complex. It has your encoder, it has the encoder area, it has your feed-forward layer, it has the self-attention. I hope some of us would have heard of what we call self-attention mechanism. So it begins to pick patterns. It concentrates on nodes. It goes to where the real features that we directly would give us or your desired results. So it focuses when you talk of self-attention, unlike you picking, the traditional CNN going through patches to form. This goes to what are those features itself that will influence better predictive capability for your models. All right, so you look at your real world transformer in action for your Google Translate. You say, how are you today? You can see working with your attention mechanism. I said, look at the student scenario. You are chatting with your friend from Korea or translating a foreign website. The transformer model inside the Google Translate translates instantly, processes the entire sentence context to provide an accurate, natural translation, not just word by word. Before, your RNN does it word by word. And if you're not careful, because our cultures are different. If you say, how are you today? The way you submit something else. But now with the work of transformer models now, it understands the nuances of language. That's what I was saying. The way Siri works now, when now I talk now, it pronounces my name very well. So it begins to understand our mother tongues are different. The way we place words are different. So how are you today in Korea might not be word for word this way. So it's beyond just saying it word for word. So it goes through the nuances. When you talk about nuances, it integrates a traditional barriers that could have hindered you from having a better translation. And so it looks at mother tongue, looks at tonation, intonations, even looks at how would I call it also stress on words and sentences. Aha. So some words when you are translating, when I'm talking to you and I have to say some things to you. So that's somebody who is speaking German. So there are some things you need to stress. If you don't stress it very well, you might be meaning something else. So now beyond just going to learn from mistake now, the transformer now takes words and translate them in basic meaning, not literally now, not word for word now. Translated to the way it will sound that whoever is reading as if he or she is talking or chatting with somebody from Korea. And when she's also, or with your friend is replying you also, it brings it back to very understandable way. Maybe you are English to Korea to English. So so it's like a feedback. You get front and back, forth and back, and things are properly aligned. So what are the limitations of your deep learning? Yes, I've been saying a lot of things. It's wonderful, it's fantastic. It still has its, what is it called? Limitation. Number one is data availability. I told you, I said models are profoundly data hungry, requiring massive and accurate labeled data to function. Yes, when it comes to deep learning, you have little data, your model could overfit or underfit. So it needs more data set to do what it needs to do. Then this issue of model complexity. I hear people saying, deep learning models are black boxes. Yes, they make it nearly impossible for you to interpret exactly why a model makes a specific. So now you begin to hear things like explainable AI, talking about GradCam and things like that. So we begin now to try, to solve this problem. We begin to try now to incorporate what? Interpretability. You hear the word interpretability or explainable AI to be able to understand what context, what exactly, or why did the model make a specific decision, or what features did the model use in making, especially when we are working with L data set. Clinicians want to know, is there a correlation between what we have done traditionally and what your model has done? So you begin to bring out those patterns. Then there's a lack of global generalization. Yes, models are excellent at narrow, highly specific tasks, but fail completely outside their training. Yes, when you can train your model and you get a wonderful accuracy, sensitivity, and specificity, they are doing very fine. Your ROC curve is doing very well. Then I bring a data from Korea and I feed my model, and my model just underfits or overfits. So you have to work on generalization. These are another problem. So I have to use what you call multi-stage classification. So I broke the classification into stages. Because when I combined, some performed very well, others didn't get a good performance. So what I did was, okay, first, differentiate between sickle cell anemia chest X-rays that has pneumonia and those that don't have pneumonia. First, which of these chest X-rays have sickle cell chest X-ray and which are normal? Then go to the next stage. Pick the sickle cell chest X-ray, check which has pneumonia and doesn't have pneumonia. Then go to the next stage, pick those that have pneumonia and look at their features to see, okay, the pneumonia, does it occur, which you call zoning. Zoning, the middle region, lower region. Then does it occur on the left lower region, right lower region? Then after that, now pick those that everything now pick and say, okay, for these that occur on lower region, what severity based on mapping what the area affected area of the lung. We now use the morphology now, affected area of the lung. So you can see that the model has been broken into pieces. That's how to stuff this. But if you stuff everything together and try to run that, some of the places will perform very well, other tasks will not perform very well. And I told them, so I was talking about limitations of deep learning. And I said one of the major limitations is your data availability. Models are what profoundly data hungry. You want to get best performance from your model, you must feed it with what large, accurately labeled data set for it to function. And I spoke about model complexity, talking about everybody you know. It's a black box, the nature of your model. I explaining deep learning to some of us are lost already. So it's impossible to actually even interpret exactly why a model made a specific decision. And I said one of the greatest solutions to this is now incorporating what interpretability, using of GradCams, which we call or your explainable AI, your GradCam, your shapely value and things to be able to understand, okay, what features actually were responsible for this decision, or what features were picked, so that you cannot correlate that with what your traditional way of doing the classification that you have done. So for those of us in the health sector, because clinicians keep asking us, how did you do this? We use these metrics and things. So we need to be able to explain that. Then I spoke about lack of global generalization. Your model could be perfectly trained. You put in data, you do everything, you test, it works fine. And you realize that I bring a data from India or I bring a data from Korea, and all of a sudden your model is fumbling. So how do we tackle this? So it's always better to train your model on multiple data sets. If possible, you can get data from more than 4 or 3 regions. But how do you do that? Because with this also there are problems or there are challenges. A lot of us don't want to share our data set. Then I spoke about incapable of multitasking, and I used my PhD project as an example. I'm working on classifying the severity classification on sickle cell patients with pneumonia. So I said it's a very, very big task. So I had to break it using what we call a multi-stage classification. So first of all, chest x-rays are gotten. You differentiate between the chest x-rays, which are sickle cell and which are not. Then you pick those that are sickle cell, then carry out another classification to say which of the sickle cells have pneumonia complication and which do not have pneumonia complication. Then you pick the sickle cell chest x-rays that have pneumonia complication and check and say, okay, at what region of the lungs is affected with pneumonia? Then when you pick those regions now, you now pick what area, what is the extent of the areas that have been affected? What is the extent based on size, using morphological patterns, or creating an heuristic algorithm to begin to now measure the mass or the size of the edges, or what is the size that has been affected. Then you say, okay, if it's between 0.1 to 0.5, it is still mild. If it's beyond that, it is moderate, and if it's above the moderate, then it is severe. Then I spoke lastly about hardware dependency. I said it earlier on. To train a deep learning model, your CPU cannot do that. You need high performance computing, which your GPU server will able to do. If not, and by the time you want to even get this, you find out that the financial commitment you need to carry out is quite exorbitant. And I was talking about the GPU I use, which I have to pay for to use when I have to do large works like that. And sometimes it costs me about $50 or thereabout. So those are the things. So as fantastic deep learning models are, they still have some bottlenecks, but I believe with time, things will begin to change and we'll be able to handle. But for data availability, all you need to do, train your model on very large data set. For model complexity, try to use explainable AI tools like your GradCam to bring out, okay, these are features that matter, these are features that did not do anything, so that you can explain. Then for also lack of global generalization, train on multiple data sets. Don't just train on data set on your region alone. Then, like I told you, incapable of multitasking, break your task into stages. Then for hardware dependency, as much as possible, you could just try. I use Kaggle. Kaggle has a 30 hours of GPU. Your Google Colab has that. Where else again? I think there's still order. If I remember, I could send to Div, then we could distribute. So you could just look for how to do that when you have to work on what? Large data or massive than this high computing, high power computing capabilities. All right. So application areas of your deep learning model. These are things everywhere now. Your Netflix and your YouTube. You have content, what's it called, recommendation and catching. Have you seen when it tells you cookies, you say accept these cookies. So it begins to learn patterns and you get to your Netflix now. Your Netflix begins to recommend, maybe you like watching horror films so much or action movies or comedy. You begin to see recommendations for you. Same thing happens in your Netflix also. Then you see your Siri or Google Assistant voice commands and it understands. You talk, it understands you, it replies you. You see your Snapchat, you can filter, you can do augmented reality, you can change your face, things like that. You have your Gmail, smart compose and spam filtering. You have things like Tesla, autopilot and self-driving features. You have your Amazon supply chain and inventory management. You have your Spotify, where you can discover weekly playlist and you can create your playlist. Then you have your Google Health, disease screening, and beyond this, you also have in agriculture, in fact, vast around all areas of field of work. So for engineers and things like that. So these are just but a few that I've mentioned here. All right. Thank you very much.